Welcome to Agronomy 2, Lecture 6, on the subject of soil and agronomy. This is part of the agronomy subject which is offered in the agricultural degree at North Melbourne Institute of TAFE, an education institution based in Australia. If you wish to find any further details about the subjects, courses or educational products that we offer, please visit our website at www.nmit.edu.au. My name is Dr. Nikki Cooley. Franklin Roosevelt was the 32nd President of the United States, and he was in office from 1933 to 1945. He was a central figure in world events during the mid-20th century, leading the United States during a time of World War, economic depression and total war. He was once quoted as saying, "The nation that destroys its soil destroys itself." I think this quote in part encompasses why we are studying soil in agronomy. On the topic of soil and agronomy, there will be two lectures, Lecture 6 and Lecture 7. In Lecture 6 we will concentrate on the physical properties of soil, that is, why structure, texture, pH and salinity are important for plants. In Lecture 7 we will go into more detail and give explicit examples of plant interactions. So let us start with the basics, a couple of definitions. Soil can be defined as the biochemical weathered uppermost layer of the Earth's crust. It is a unique ecosystem and an essential resource for the production and growth of plants and crops. This definition comes from the Schaefer and Monacade 2009 Introduction to Agronomy, Food, Crops and Environment textbook. A second definition I'd like to introduce you to is one from the Science Glossary, that is the Soil Science Society of America. Here, soil is defined in two parts. Part 1, the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of land plants. Part 2, the unconsolidated mineral or organic matter of the surface of the earth that has been subjected to and shows effects of genetic and environmental factors of climate, including water and temperature, and macro and microorganisms conducted by relief acting on parent material over a period of time. A product soil differs from the material from which it is derived in many physical, chemical, biological, and morphological properties and characteristics. While the second definition is a lot longer than the first definition, it does encompass all the properties that soil has. It also gives us an insight as to why these properties may be important to plants. In this lecture, I am going to introduce to you some basic concepts. I am doing this to ensure that these have been covered, although many of you will have explored many of these concepts in much more detail in the other subjects that we offer as part of this degree. Please ensure that you read on your notes on soil and water and soil and nutrition, as these will help you and build on your understanding of soil. So if you would like to characterize a soil, it is always good to start with the soil type. The principal soil constituents to consider for identification of a soil are texture, structure, pH and salinity. I'd like to start with exploring acidity and agronomy. Acidity is a chemical composite condition of the soil and is measured on the pH scale. The scale ranges from 1, which is strongly acidic, to 12, which is strongly alkaline. Acidic soils have a pH of about 4.5 or below. This is when the soil acidity is measured in the solute calcium chloride. Soil acidity can reduce yields. So what are the consequences of a soil that has a low pH or that is acidic? Well, there are a number of effects that may be seen. Low pH can prevent legumes from nodulating. This has impacts on nutrient levels in soils, particularly that of nitrogen. Low pH soils can reduce recycling of nutrients by beneficial soil microorganisms. Acidic soils can increase toxicity to plants by the release of aluminium from the soil, and toxicity can be experienced by high manganese levels resulting. This is common in hot, dry and poorly drained soils, all of which can be found in Australia. Low pH soils normally result in a decline in nutrient availability. Available aluminium and iron may tie up valuable nutrients such as phosphorus. They can cause molybdenum deficiency. There are a range of effects that can be seen from these acidic soils, as described in the previous slide. However, different crop and pastures are affected differently by different aspects of soil salinity. Soil salinity can affect the top 10 centimetre of the soil, or it may be a problem that occurs below the soil, that is the subsoil level. The top 10 centimetres is the more common. Subsoil acidity costly and is difficult to adjust for. The figure on the slide is from Pastures Book 5, compiled by the New South Wales Agriculture. It is a figure that summarises how pH can influence soil fertility and nutrition availability. We know that soils are ideal at neutral or pH 7. You can see from the slide here that it is marked as the optimal pH. As you increase the pH or alkalinity, you can see how some components become toxic. And then if you have a strong alkalinity, you have deficiencies of iron, manganese, zinc, copper and boron. You can also have an excess of sodium in these higher pHs. As you reduce your pH or your soil becomes more acidic, you can have a result of excess of aluminium and manganese iron. This may result in a deficiency of magnesium, calcium, potassium, phosphorus and molybdenum. The figure on this slide is another visual representation of the relationship of pH and the availability of essential elements to plant growth. The larger the area in black, the more mineral present at that pH. Therefore, if you look at pH 7, you will see that most compounds are freely available: nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, boron, copper and zinc and molybdenum. As you reduce the pH, some of these components, such as phosphorus, calcium, magnesium, become less. As you increase the pH, other compounds, such as manganese, iron, boron, copper and zinc, are reduced. Different plants and different crops are influenced differently by pH. Some plants are tolerant to low pHs, while others are not. Table 1, compiled by David Brower, 1994, from the Pasture Book 5, New South Wales Government, Agriculture, is a summary of some plants and how tolerant or how acidic they are. For example, you will see lucerne and barley is highly sensitive to pH, while crops such as couch grass and lotus are very tolerant to low pHs. You will also notice in this table that the critical acceptability to aluminium is quoted too. Aluminium toxicity seems to be associated with the response of the plants to low pH. Biological activity is important in the breakdown of organic matter and is also linked to the percent carbon in the soil. Microbial activity makes up for the majority of biological activity in a soil, as can be seen from the diagram on the slide. Microbial activity is highest in the root zone, reducing as you go lower. pH can influence microbial activity. Microbes form mineralization of organic matter, are most active between the ranges pH 6 to pH 7. The USDA showed a ton of microscope bacteria may be active in each acre of soil. So can plant roots affect soil pH immediately around the roots? Well, this is an interesting question, and one that was looked up or investigated by Roldoff et al. In 2013 in the following paper, Spatial Temporal Mapping of Local Soil pH Changes Induced by Roots of Lupin and Soft Rush. I'd like you to read through this paper and answer the following questions to complete your notes on this subject. Question 1. What was the technique developed that allowed researchers to investigate root pH in situ? Question 2. There were 3 significant findings this paper made to add to our understanding of root soil pH. What were they? And question 3. How might you use this information in your cropping management? Please complete the answers to these questions to complete your notes on this area. So what causes soil acidity? We would just touch on this, but it will be covered more in the soil and nutrition and soil and water subjects. Natural leaching can cause soil acidity. There is a high association with nitrogen fertigation and leaching of nitrogen. The nitrates then increase the acidity of the soil. Annual subclover pastures or grain legumes, excess nitrogen fertilizers, and the removal of alkaline plant and animal waste materials from the paddock. Organic acid build-up from increased levels of soil organic matter. Natural leaching can occur over thousands of years, or a soil can become acidic in a short time. This tends to be seen when you have such components as excess nitrogen fertilizer. Some common soil acidity symptoms are listed below. Uneven pasture or crop growth. Pay attention to the plants or crop species that you plant that are acid sensitive. You may see an invasion of weeds that are acid tolerant. Look below your soils, look at your nodulation of your legumes. If they are poor, soil acidity could be contributing to this. Do you have stunted root growth, or have you seen an increase in root disease? These too indicate acidic soils. Do you have difficulty in establishing either crops, lucerne, medix or farris? The formation of organic mats on the soil surface as a result of less biological activity may also be a sign of acidic soils. If you do see or suspect acidic soils, what action can you undertake? I would begin with a soil test. Test the pH and the aluminium levels, but be mindful that there are several tests out there and that the differences may involve different interpretation. That is, if you do a soil pH test in water versus a soil pH test in calcium chloride, you will see differences. The calcium chloride test usually gives a more acidic outcome than the water. There is a significant amount of variation in soil pH across any paddock. In order to account for this natural variation, to detect if there is a real problem, it is advised that you do a minimal of 20 samples from the paddock. It is important to note the sampling time, temperature, and water content. If you have variations in temperature and water content, this will influence your pH, and therefore a comparison may become difficult. One of the most common and popular treatments of pH is the application of the substance lime. This needs to be spread evenly over affected areas and incorporated into the soil. The mode of action of lime is that it changes the pH by neutralizing the surface. As a guide or rule of thumb, 2 tons per hectare is required to change 1 pH unit. However, the required concentration will depend on your soil texture. If you have a heavy clay or a clay loam soil, you will need more. pH maintenance. Once you have established a reasonable pH, it is advised that you then apply lime at 1 ton per hectare every 8 weeks. There is a method of test strip application of lime that you can apply that was developed by G. Fenton in 1993. One of the actions you could consider is to do nothing, and certainly doing nothing is a consideration for some agronomical problems, particularly when you're growing to a high commercial output. However, I would not recommend this with pH issues. Plant yields will continue to decline if you do not do anything about them. If you allow your soils to become very acidic, it may be hard to control and could be more expensive in the long run. A second action is that you could grow more tolerant species. This may assist you while you're increasing your soil pH. If you do only this, that is, only grow tolerant species and do not try to address the issue of low pH, acidification will continue. At some point, your pH tolerant species will stop providing good yields. Another advisable action to consider is your farming system. Can you change your farming system and reduce your intensity? For example, a lightly grazed underdeveloped pasture in acid soils may need a lime application as low as 0.5 tons per hectare every 10 years. Intensive production systems, high cropping yields, hay cutting areas and productive pastures will need 3 tons per hectare every 10 years. Therefore, management should be considered carefully. You can reduce your nitrate by managing your nitrogen. You can also manage your soil moisture and increase the perennial pastures and deep-rooted plants. The last 3 actions will not assist if your soils are already too acidic, but they will enable long-term stability of your pH, of your soil pH, that is, once you have your issues under control. Now let us consider soil structure. Soil structure is the volume and the arrangement of pores in the soil. This determines soil water movement and airflow into the soil profile. This affects soil friability, that is, the ease of rain infiltration and runoff, cultivation and growing plants. There are essentially 2 types of soil structure problems that may occur. There are those that exist naturally in the soil. They are often difficult to fix. An example of a naturally occurring soil structure problem is high sodium ions relative to the other elements in the soil. The second type of soil structure problems are due to the farming practice, and these include excess cultivation, which results in crusting, compaction, plough, poor grazing practices. Livestock is responsible for much of the soil structure damage that occurs when management is an issue. Pulverized soil is the destruction of large and small soil channels. These allow rapid air and water infiltration and are very important in healthy soils. If you run livestock on wet soils, you can increase compaction and breakdown of soil aggregates. Organic matter is important as it contributes to the binding of the soil. Soil structure erosion. Low organic matter collapses in wet conditions. Reduction in infiltration and increased runoff can occur. 5 to 10 times more erosion will occur when poor soil structure exists. I'd like you, next time you're at the Yang Ying farm on paddock 7 in the demonstrator, to look at where the livestock grazed some of our plots. Observe any issues of compaction or pulverized soil that you may be able to see. How would you correct for this? Are the problems that you're seeing significant, or are they minor? Identification of poor soil structure can be obtained from seeing or observing some of the following. It is always wise to look in the areas you suspect that you have a problem and compare them with similar soils where you suspect good structure exists. You know, soils where you haven't run livestock on, for example. Rill and sheet erosion are processes where water runs over the soil surface and strips away sheets of soil only millimeters at a time. Water will then collect. Small eroded channels form down the slope. Surface crusts are an indication of poor soil structure. These reduce infiltration of water and restrict seeding emergence when they become dry. Cloddiness. This is after a single cultivation and where brick-like clods are formed. Further cultivation is required to produce a suitable seed bed. Some plants can be used as indicator plants. That is, their presence suggests poor soil structure. The toad rush, for example, Juncus bulfonius, grows where water has ponded on the surface. Ponding is the process where water accumulates after a light rain. Water does not sink or penetrate into the soil. Hard surface can be detected during periods of dryness. If you use a pickaxe, you can see how far you can penetrate this into the soil. If you have poor soil structure, you will not be able to penetrate your pickaxe far. Poor infiltration. This is seen after first rains after a dry spell. See how far the water has infiltrated into your soil. And finally, the presence of organic matter. The soil tends to be brittle and paler in colour because organic matter tends to be dark. So what action can you undertake to ensure or correct for your soil structure? The establishment of permanent pasture is considered the most effective mechanism for solving many soil structure issues. If you have established a permanent pasture on soils of poor structure, it is advisable that you manage these pastures well and pay particular attention to your water, your nutrients, and ensure that only light grazing occurs. If the soil is naturally unstable, it will result in poor structure, and this may be treated by the application of gypsum. If you suspect this, it is best to test for both slacking and dispension. If you see positive results for dispension, then it is likely that gypsum application will be helpful. The recommended rate in most situations is 2.5 tons of gypsum per hectare. Gypsum supplies calcium, which displaces sodium from the clay surface. An exchangeable cation level test will indicate your correct application rate. Another possible action for increasing your soil structure is to add fauna. These are small animals that can improve soil structure by contributing to the physical breakup of the soil. The most common and readily used are that of the earthworms. They play an important part in contributing to healthy soil structure, and they are also involved in the recycling of nutrients. trials have demonstrated that a 40% increase in pasture production via increasing nodulation can result from earthworm application. Yields of wheat have been shown to increase by up to 35%. If you do wish to add earthworms, it is worth noting that they fall into two groups. There are those on the surface and the subsurface. It is advisable to obtain the subsurface worms rather than the surface worms. The surface worms specialize in the breakdown of components on the surface, like leaf litter, while the subsurface ones will be more effective at increasing your soil structure properties. There are other beneficials as well. The image of the slide is from a cryptostigmatide mite. This is a beneficial flora and can help with the breakup of soil and add to soil structure. The prostigmatite mite on your slide is another example of a beneficial flora. And the final mite beneficial flora I will show is the mesostigmatide mite. Springtails, of which there are many examples, are another good beneficial flora. Again, it is their physical action of breaking up the soil that adds to the soil structure characteristics. It will probably not surprise you to learn that there is a long list of beneficial fauna, all which help by their movements to break up the soil and add to a good structure. These include such creatures as the millipede, landhopper, polyexonoid, symphylan, the geophilomorph centipede, the woodlouse, the adult caribid beetle, the scarabid, the weevil, the leptopteria larvae, and the encocephalid bug, as well as soldier and worker termites. As a task, see if you can identify the images that I have placed on this slide. There are 6 in total. On the slide is an image of the summary of the macro soil fauna. As you can see, there are many communities that contribute to the soil structure. It is good to have a diverse selection of beneficial organisms. The role of beneficial fauna is one of a physical nature, where these creatures are able to shed organic residues. These residues are then able to infiltrate into the soil. The soil fragments are then broken down or decomposed by microbes and fungi. It is important to check for soil fauna diversity. You want to check between the ratios of predators and beneficial organisms. Ground cover is not bare or loose soil or scades or clay pans. It is, however, live plants, sticks and logs, litter, dead plant material, rocks and stones, dung, soil crusts, and cryptograms and lichens. It is important for you as agronomists to be able to estimate ground cover. Ideally, you can use the ground cover to reduce soil erosion. The image on the left-hand side of your slide is of a ground cover representing 20%, while the image on the right-hand side represents 80% ground cover. These images were sourced from DPI ground cover measuring tool, which can be found on the web on Moodle. There is always a balance between erosion control and animal production. The more animals you have on your pastures or crops, the more erosion will occur from the structural damage that occurs. Many natives are excellent ground cover, but seem to be poor for animal production. A crop such as lucerne is high for animal production, but is not as good as a perennial grass for erosion control. Introduced pastures seem to be a good compromise, as they are both good for erosion control and excellent for animal production value. You may wish to consider a native perennial grass system. However, if you do, you need to consider the ground cover that you can achieve A 70% ground cover, which is normal for introduced pastures, may not be enough to feed your livestock. Therefore, pastures need to be carefully managed with respect to reducing the overgrazing that may occur. Now let us look at soil erosion. The initial signs of soil erosion can be sheet or rill erosion. To avoid soil erosion, it is advisable not to let your ground cover fall below 70%. This, of course, is dependent on where you are. This ratio will change if you're on tablelands versus floodplains, for example. The ground cover reduces soil loss and rain runoff. Tillage practices should also be considered when considering soil erosion. Management practices such as fertilizers and stock numbers need to be considered, and much attention should be spent on managing correctly during periods of stress, such as a drought period. Soil salinity is an increasing problem in Australian farming. There are predominantly two types, that of dryland salinity and salinity caused by irrigation issues. Salinity is the build-up of salt in the soil surface resulting in the rising of the water table. This is often followed by groundwater seepage. This process is called the saline steep. The causes of a build-up of salinity include land clearing, that is the removal of native trees, shrubs and perennial grasses that die out. Traditional farming practices using clovers and pastures have resulted in higher levels of water in the subsoil, and this has assisted in the problem. The higher water table that results release salts that are normally locked up well below the soil surface. These salts are drawn by capillary action to the surface. The picture on your slide was taken from a high salinity area around the Murray-Darling region. It was taken by DPI. The effects of salinity on plants depend on the degree of the salinity. At best they reduce yield. At worst they are toxic to plants. They can also induce waterlogging, which is a secondary issue, and this again can result in significant loss of yield and death of the plant if the situation is severe. The following paper, written by Wadji et al. In 2013 on the effects of phosphorus in alleviation of adverse impacts of salinity on wheat grown on different soils, is some recent research published in 2013. In order to complete your notes on this topic, please write a paragraph on the main findings of the research. State what the adverse effects on wheat were and how were they alleviated by the addition of phosphorus. Would you use this knowledge would you use the knowledge from this publication in your farming systems, and if you would, how would you apply it? When water is in the soil, it is not used. Deep drainage to the water table increases, and this can have an impact on salinity. Native trees are very effective at using this wastewater, and removing them reduces the capacity and again leads to salinity issues. Annual crops and pastures with shallow-rooted vegetation systems, and they do not use deep water, again leading to susceptibility of salinity. Overgrazing, reduced leaf areas, lowers plant water use. Again, this can lead to salinity. Sowing date. If the paddock is not using water in the autumn, this again can add to the problem. Poor crop and pasture use can lead to disease and inadequate use of fertilizers, or any factor limiting plant growth can increase the chances of salinity. Long farrows. Farrows aim to store water, and often soil is full before the crop is sown. Additional rain recharges the groundwater and again can result in higher salinity. Leaking dams, perhaps an obvious one, but as the water leaks through the dam, this again increases the water table, which can bring up the salts, which results in salinity. Poor surface drainage can also add to salinity issues. Water lying on the land powers plant growth and water use. This then leaks to the water table. Careful management of salt-affected land can stay productive. Here are some suggested actions. Fence off the area that is affected by the salinity from the rest of the paddock. Provide good surface drainage and prevent additional runoff water that may cause erosion by protection the affected area with a bank. Plant saltbush if the site gets wet. Control unwanted species such as sea barley grass. Sow productive species such as Pinsilia, strawberry clover, tall wheatgrass and saltbush. Keep stock off for at least 1 year and ideally aim for 2. Crash graze during summer or early autumn once salt-tolerant species have been established. And finally, while you are managing the soils, it is important to remember that you are managing ecosystems. We have touched on some of this with respect to soil structure. However, these relationships are far more complex than just what occurs in the soil, and they do involve birds and mammals as well. This brings us to the end of this lecture. In summary, we have defined soil, explained its components, and understood that it is a complex ecosystem. We have explored and understood the impacts on crops, how to manage these impacts, and how to avoid these issues. We have looked specifically at acidity effects, soil structure, and salinity. Testing, and therefore understanding your soils, will avoid significant issues and allow optimal profit.